Jnanam Paramam Dhyayam. Knowledge is supreme.
Today I will have more consequences from the refined version of NNL. And the first theorem we will prove is, if K is a field, then the polynomial ring in n variables or K has dimension n. That means we need to prove that there is a chain of length n plus n in the spectrum of this polynomial algebra, and every chain of prime ideals in this should have length at most n. So, first I am trying to produce a chain of length n in the spectrum of the polynomial algebra. So, for that observe that 0 is a prime ideal, ideal generated by x1 is a prime ideal, ideal generated by x1 x2 is a prime ideal, and so on, ideal generated by x1 to xn, these are all prime ideals. The easiest way to check that these are prime ideals is just go mod that and check the ring is an integral domain, and in each one of these cases actually the residue class ring is actually the polynomial ring, therefore it's an integral domain. So, and the chain is at no place there is equality, so it's a chain of length n. So, therefore it's immediate by definition of the dimension that dimension of kx1 to xn is n, less, bigger equal to n, because this is a chain of length n. So, the dimension is a supremum, therefore this dimension is at least n. Conversely, I want to prove that every chain has length at most n. So, start with arbitrary chain P1, P0 contained in P1 and so on, contained in PR. This is a in spec of kx1 to xn. This has length r, and we want to prove r is less equal to n. So, to prove r is less equal to n. Now, I am going to apply Nagata's version of NNL to this chain, and the ring A is the polynomial ring, this, and this is a chain in that spectrum. So, Nagata's version will say that I will find an elements y1 to ym in these which are algebraically independent, and when I contract this chain of prime ideals to that, it will be generated by the variables. So, there exist, so B is k y1 to yn so that this is integral, and y1 to yn are algebraically independent, such that P0 intersected with B, this is generated by y1 to y, I will use the same notation h0, then contained in P1 intersection B, this is also generated by the variables y1 to yh1 and so on. And because this is an integral extension, if this chain is proper, then the contracted chain is also proper, because the integralness. So, that is, so the last one is this P R intersected B. This is Y1 to YHR. So here just observe that I have used the same n that I explained last time, because of this integralness the transcendent degrees are same, and therefore it is the same n. So therefore because the chain is proper, the h are increasing. H of I plus 1 is strictly bigger than h of I for every I 0 to whatever r. So we get a chain like this: 0 less equal to h0, strictly less than h1, strictly less than hr, which is less equal to n, because the number of variables is at most n, and h are increasing. So therefore r is less equal to n, and therefore dimension of A is less equal to n. So that finishes the proof, right? So the thing to note that is, from the classical version of normalization lemma, we could not have deduced this, because we needed a refined where for the chains. That was the reason I proved that first. Okay. Now the next observation is also very important. This in fact shows that the dimension of a finite type K algebra is finite. From the definition of a dimension, it is not clear a dimension is finite or not. But so A is K algebra of finite type. Assume that A is an integral domain. Then the dimension of A is transcendent degree of A over K. When I write this is by definition transcendent degree of the quotient field of A over K. Quotient field of A is an field extension of K, and last time I recalled what is the definition of a transcendent degree of a field extension. It is the number of algebraically independent elements, so that when you join them you get an algebraic extension of a quotient field is an algebraic extension of this purely transcendental extension. So proof. So this in particular says that the dimension of finite type K algebra is finite. So because this transcendent degree is finite, because the quotient field is finitely generated field extension. So therefore the transcendent degree can at most be the number of K algebra generators for the algebra A. Okay. So by normalization lemma, we can find algebraically independent elements K x1 to xn such that this extension is integral, and these are algebraically independent elements. So this is a polynomial algebra. Let us call this as B. We have noted last time that whenever you have integral extension, then the dimensions are same. So therefore dimension of A equal to dimension of B, but B is a polynomial algebra because x1 to xn are algebraically independent. Therefore this is n by earlier theorem. and this n is nothing but the transcendent degree, because in this case the quotient field of A, when I go to quotient field level, quotient field of B, this is rational function field in n variables, and quotient field of A is here, and this, because this A is integral over B, this is algebraic extension. Therefore, indeed this x1 to xn is a transcendence basis. So, x1 to xn is a transcendence basis of QA over A, and we have stated that any two transcendence bases have the same number of elements. So, therefore, transcendent degree of QA over K is n, and just now we have put this n is the dimension of A. This is very, very important for those who want to study algebraic geometry. When we have enough language, next time I want to do little bit of language from algebraic geometry, because one cannot really avoid it. So, it is better that we do it from the basics first, and then some more consequences which are geometric in nature, that we will write down. Okay. Now, the next one is also very important theorem for many things. So, again K is a field and A is finite K algebra of finite type. This also sometimes I call it affine algebra over K. And suppose we have a prime ideal P. Let us assume also A is an integral domain. Assume that A is an integral domain. So, let P be a prime ideal in A. Then we have these two numbers attached to this P. One is height P and the other is dimension of the residue class ring. So, height P is by definition, you take the chains of prime ideals which will end at P. So, P0 contained in P1, etc., etc. PR, which is P, this is a length of R, length is R ending at P, and you take the supremum of such R, that is called the height of P. On the other hand, we have also this dimension of the residue class ring. That means you start with a chain at P and take, this is a chain of prime ideals in A, in spec A. And if you take their supremum here, that you get a dimension of the residue class ring. So, we want to know what is the relation between the three numbers, dimension A, height P and dimension of A by P. And obviously, if I take the chain which ends at P and continue with this chain, obviously I am going to get a chain of length, their sum. So, therefore, dimension is at least the sum, but the assertion here we want to prove is actually it is equal. So, this is 4. So, the assertion is, so then dimension of A equal to height P plus dimension of the residue class ring A by P. Proof? As I said, it is clear that dimension of A is bigger equal to height P plus dimension A by P. So let me give this height P as the name H. I want to prove the reverse inequality. So I am going to apply Nagata's version of NNL. So apply Nagata's version of NNL to A, to the ring A. So you need a affine algebra A, that is A, and I need a chain also. So but I chain I just take P, just only one element, so it's a length 0 chain. So Nagata's version will say there exists a polynomial ring inside this, so that is, let's call it B, is k x1 to xn, and this is integral, such that this P, when I contract to B, it is generated by variables. So P contracted to B is generated by x1 to xr. This is a polynomial ring, polynomial algebra. That means x1 to xn are algebraically independent. This is for some r. Bigger equal to 0. First of all, note that the dimension of A is n. Because this is integral. And now the next thing to note is this B is a polynomial algebra. Therefore, note that B is an integrally closed domain. Polynomial ring is a UFD and UFDs are integrally closed. That is maybe the shortest, right? So it's integrally closed and integral homomorphism. Then I want to say the going down holds. Going down theorem holds for this extension A contained in B. See, last time I recalled what is going down, right? So the going down theorem, one of the consequence there is, if I take the prime ideal P in A and contract to B, then the height will not change. So in particular, if P is a prime ideal in A and if I take Q to be equal to the contraction of P to B, then height of P equal to height of Q. This is very simple to check from going down. But height of Q is height of Q is generated by x1 to xr, because when we have chosen this extension so that contraction of P is generated by x1 to xr. So this is height of ideal generated by x1 to xr, which is r. That is because you definitely have a chain. So this one, you definitely have a chain which starts at 0, ideal generated by x1, ideal generated by x1, x2. This is a proper chain all the way to ideal generated by x1 to xr. So therefore, height of this Q is at least r. But on the other hand, I want to check that the height is exactly r. So what we need to check now is height of Q cannot be bigger than r. If it is bigger than r, then we should get a contradiction. Okay. So, if height is bigger than r, then look at dimension of B, which is bigger than equal to height of Q plus dimension of the residue class ring B by Q. But we are assuming height of Q is at least r, so this is strictly bigger than r, and this residue class ring is a polynomial ring in n variables mod the ideal generated by polynomials up to x1 to xr. So, it will disappear, the variables x1 to xr will disappear, and the remaining variables will be xr plus 1, xr plus 2 up to xn, and those are n minus r in number. So, this dimension is n minus r. We have proved that the dimension of the polynomial ring over a field is the number of variables. So, this is at least this is exactly n minus r, which is n. So, this shows that the dimension of B is strictly bigger than n, but that is not possible because dimension B is n. So, not possible. So, and what is the dimension of the residue class ring? Dimension of A by P, this is dimension of B by P intersection B, because when I go mod I get an integral extension. This is because A by P and this A B by x1 to xr. This is an integral extension. This is integral. Because the original extension A to B was integral, so I just passed on to the residue class rings. So, this is integral, therefore, dimension of this equal to dimension of this, and dimension of this is exactly n minus r, because this B1 to the residue class ring is nothing but k xr plus 1 to xn. So, therefore, when you add up height of P plus dimension of A by P, height of P is r. Oh, I messed it up, I called it h sometime. So, please correct here, this is not h, this is r, let us call it. Okay. So, therefore, this is r plus this is n minus r, which is n, and which was nothing but the dimension of A, because again integralness. So, that proves the theorem, right. Okay.